billions of tiny particles move around you. This invisible motions runs our phones and powers our world. We call it electric current. The wire is already full of electrons. Turning on a switch doesn't create them. It simply makes the electrons already inside begin drifting together. Here's something surprising. These electrons always drift from the negative terminal toward the positive terminal. But that's not the direction we usually call current. The reason is simple. Before electrons were discovered, scientists assumed electricity flowed from positive to negative. Does this flowing current affect the space around the wire? For many years, people thought current simply flowed through a wire, nothing more. But in 1820, one unexpected experiment changed physics forever. Hans Christian Ørsted placed a compass near the wire and turned the current on. Instantly, the compass needle began to move. Ørsted repeated the experiment again and again. Every time current flowed through the wire, the compass needle moved. It was no coincidence. The only possible explanation was that the current had created something around the wire, something invisible. Scientists called it a magnetic field. Unlike an electric field, this magnetic field doesn't point toward or away from the wire. Instead, it forms complete circles around it. But how can we know which way these circles go? To understand the magnetic field, scientists placed the compass at different positions around the wire. At every new position, the needle pointed in a different direction. When all these compass directions were combined, a beautiful pattern appeared. The magnetic field wasn't pointing outward or inward, it formed complete circles around the wire. Scientists tested one more thing. They reversed the direction of the current. This time, every compass needle turned in the opposite direction. Repeating this experiment every time would be impractical, so physicists created a simple shortcut to predict the field direction, the right-hand thumb rule. Point your right thumb in the direction of the current. Now curl your fingers. The direction your fingers wrap around the wire is the direction of the magnetic field. This rule works every time. If the current is reversed, the thumb points the other way, and the direction of magnetic field also reverses. Now imagine bending the same wire into a complete circle. The current still flows, but the magnetic field changes in a remarkable way. Now watch what happens when we add more loops. Each loop creates its own magnetic field. Together, these fields combine to produce one much stronger magnetic field. A coil made of many closely wound loops is called a solenoid. It produces a magnetic field much like a bar magnet, but much stronger than a single loop. Now, place a soft iron core inside the solenoid. The magnetic field becomes much stronger. This combination is called an electromagnet. Now, why does the soft iron core make the electromagnet stronger? The answer lies deep inside the iron itself. Inside every piece of soft iron are countless tiny magnetic regions. Each one behaves like a tiny magnet. These regions are called magnetic domains. Normally, these magnetic domains point in different directions. Their magnetic effects cancel each other, so the iron does not behave like a strong magnet. When current flows through the solenoid, its magnetic field makes many of these domains turn in the same direction. Their magnetic effects now add together. Switch the current off, and the solenoid's magnetic field disappears. Without that field, most magnetic domains return to random directions. That's why it's called an electromagnet. It acts like a magnet only while electric current is flowing. Switch the current off, and its magnetism almost disappears. We began with a simple current-carrying wire, then a loop, a solenoid, and finally an electromagnet. A small electric current can create a powerful magnetic force.